Okay, so now what we're going to do is we're going to ask a question of how much precipitates. And these kinds of problems, really what you're given is you're given starting with, right? You know, concentrations of ions are given. And then you're assumed the second thing that happens is precipitation takes place. And then because of the magnitude of the Ks for these kinds of problems, uh, essentially most of one ion will precipitate. So the difficulty in these problems is they often ask how much of a particular ion remains, right, after the precipitation takes place. And it turns out this is like a horribly hard problem for your calculator to solve. It's not that you can't solve it, but it turns out it's a really hard problem for your calculator to solve. So I'm going to tell you the process in general. I'm going to give you an illustration of why this is the way it is, and then we'll talk a little bit. We'll actually do a problem. We'll talk our way through like doing this, okay? So the first thing that happens is to do this problem is we're going to set up a double ice table. And in the first part of the problem, it's really not an equilibrium. It's just a mole calculation for a limiting reactant. And we're going to figure out what the concentrations would be if one of the ions completely precipitated out. Okay? So this is the idea. The first half, there's like two halves to the ice table. The first half is to calculate what they would say is stoichiometric precipitation. But really all that means is we're going to calculate so that one of the concentrations goes to zero. That's supposed to be that. I put that. So that one ion concentration goes to zero, okay? And then the second thing we're going to do is we're going to calculate back to equilibrium. And I'll explain to you why I say back to equilibrium. That's the term I use in a second. Okay. And that's actually that part. Once you assume that one of the ion precipitates out completely, then what we do is we're going to calculate back to the equilibrium. That part will actually be a real ice table. You'll have initial, you'll have a change, and an equilibrium. The first part of the ice table, I usually do this in moles, right? And moles aren't what we use in ice tables, but I do moles because usually the numbers are nicer. It's easier to deal with. The numbers are usually nicer. So let me explain to you what the problem is in doing these kinds of calculations and why we go through this process of like doing two steps when before one step worked pretty good. So I'm going to give you a sort of a number line version of KSP. It's going to look like this. My number line is going to go here to here, okay? And I'm going to have 0 over here. And I guess if essentially I have infinity over here. And what this number line actually represents, it's all the possible values of Q. Okay, so that's the product of the ions raised to their stoichiometric coefficients in terms of powers, right? And what do you know about KSP? You know KSPs are really small. So Q represents all variations of concentrations, right? But regardless, KSP is a small value, so Q will be equal to K way down here somewhere. Now, this is where solutions will eventually end up going to. The concentrations will be changing during the course of the reaction, and over time, the concentration will change in such a way so you go back to KSP, okay? Well, what does it mean that you're given concentrations of ions at the beginning, right? It means really, if it's a precipitation problem, that the Q value is bigger than K. So reality is you're starting over here somewhere. Okay. Now, when precipitation starts taking place, concentrations will be going down and be eventually approaching Q, right? And this, if you set it up as an ice table from the beginning, this would be X. The change in the value you get for the concentration, right? That's related to X. Now, it might be 2X for one, it might be X for another, it might be 3X, right? But anyways, it's related to X. So, let's say this is a number like 0.1. Like, in terms of like molarities, let's say everything came out to be like 0.1 molar. Again, right, this is Q, so you would have to do all the calculations and stuff. But let's just pretend we're not. And it's just going to call that what 0.1 molar looks like on this scale. In the end, this concentration that we get can be really small. It's not unusual to have it to be like 10 to the minus 20. It's small, okay, because KSP is small. So think about what that means, right? I'm going to take 0.1 and I'm going to subtract a value from X from that, right? So 0.1 is where I'm starting. I'm going to subtract a value for X from that. And I'm going to be left with 10 to the minus 20, 10 to the minus 30, 10 to the minus 40. Some really, really tiny numbers come out of these calculations. But in some instances, that number is what you're looking for, that really tiny number. So why is this a problem? It's a problem because your calculator only carries about 12 to 16 digits in its memory. So when I take 0.1 and then something that's different from 0.1 by 10 to the minus 20, you get 0 out as the answer. And it's not 0 because you can actually, like in most calculators, just randomly enter that number and subtract it, but it'll get the same number back because basically the calculator doesn't keep track of that many places, because who needs that, right? Well, it turns out sometimes you need that. Okay, so what do you do, right? I think even Wolfram Alpha doesn't carry that many digits, right? So even the more advanced things don't. This is what you do, is you just say, okay, let's just let it all precipitate out. So one of the ions completely precipitates out. So I'm starting over here. I'm going to change my color here. I'm starting over here at 0.1. Okay. And I'm just going to go all the way down here, past KSP to 0. So there I'm at the 0 right there. And then I need to get to equilibrium. It's still here. And this is X. Oh, I'm trying to write too small at the bottom of the string. This is X, this little tiny number, when you come back in this direction. But you're not subtracting it from anything, so it's okay that it's a tiny number because you're not trying to get the difference between two numbers. They're just different by like 10 to the minus 20, okay? So your calculator can handle that problem, but it can't handle going the other way. Here's the other thing, the big advantage that this approach gives you. Everything can be approximated at this point because X, you designed the problem so X would be small, okay? And so since X is small, you can assume X is approximately equal to 0, right? And you can use the X is small approximation. Okay, so let's go ahead and do a problem, sort of put this all into place. But that's the concept, okay? We're going to go assume it all precipitates, and then we'll come back to equilibrium. All right, so I have, what are the iron and hydroxide ion concentrations that remain when 2.500 milliliters of 1 molar of sodium hydroxide and 20 milliliters of 0.5 molar iron nitrate are mixed? Then it's a OH precipitation, hydroxide precipitation, so you need to know like what your reaction is, right? So I have Fe, OH2, that's a solid, right? So it breaks up into its ions, like this. And you know that the iron is going to come from this solution, and the hydroxide is going to come from this solution. And there's only one iron This is one of the things I hadn't mentioned yet. There's only one iron in that formula, so the molarity of the compound is the same as the molarity of the ion. And the same thing is true here. The molarity of hydroxide will be the same as the molarity of sodium hydroxide at mixture, so when you mix them, okay? So what I'm going to do now is I'm going to set up my first ice table. I'm going to have an initial and a change, okay? And that's all I'm going to put there for now. Now, you, like, when you do these problems, you could write more because you'll have seen what I'm doing here. Oh, and I wrote it underneath here because this doesn't matter, right? It's a solid. So I have my line over here. And you've seen me kind of do that cheat before, I think. Okay, so now what am I going to put in here, right? And it turns out what I usually like to do in this first set is to use millimoles. Normally the numbers in millimoles are nicer than the numbers in molarity. And I'm going to use this first table to figure out which one's the limiting reactant. Okay, so this is starting far to the right of equilibrium on my number line here somewhere. And I'm going to go far to the left on my equilibrium. Okay, so how many millimoles of iron are there? Okay, let's do that. Millimoles of Fe. Well, that's going to be 20 times this number, 20, right? Milliliters times 0.5 molar. I'll write this one out. That's what? 10. That's millimoles. I didn't leave enough room, but I might run out of space, so I don't want to run out of space. So I'm going to cram it all into a corner. Now, for the hydroxide, same kind of calculation. And in order to do that, right, I have, let's see, 25 times 1. So that's 25. Nice. 3 sig figs. All this is 3 sig fig stuff. Like that. Okay, so those are my starting amounts, so I can put them up here. This is all going to be millimoles, so I just write a little note to myself like that, and I make this one 25, and this one's 10. And the change is going to be still minus x, right, and minus 2x, because that's the coefficient. And then what I'm going to do is I'm going to do an assumption that the reaction is going to completion. All right, so what does that mean? Well, it means one of them goes to 0. And whichever one goes to 0 actually tells you how much precipitates formed, okay? So, for example, in this one, if I make x equal to, let's say I make it equal to 2x equal to 25, right? Then I get 12.5 for x. That is, if I'm assuming this goes to 0. Well, if I assume that, then this is going to be negative. So that can't be, hydroxide can't be the limiting reactant. Most of the time, if you just look at it, you can tell. So I take 25 divided by 2, and I get 12.5. I take 10 divided by 1, that's the coefficient here, and I'll get 10. So that's my limiting reactant. So this is 10. 0. Sorry, it's 10. X is 10. Since x is 10, right, 25 minus 2x is 5. So I'm down to 2 sig figs. Yay. All right. Again, that's millimoles. So I usually just call this final. You occasionally see me put F in there, but that's because it's the final millimoles. But watch what we're going to do. We're going to make that the initial for my second ice table. And the way you do that is you divide by total volume, which is, in this case, 25 plus 20, which is 45 milliliters. Now, I know that bothers you, right? I don't know, get over it, I guess. But you can also, I just did that to illustrate. That's equal to, if you take 5.0 millimoles, right? Sorry. Been a long semester. We're only halfway through. 45 milliliters, right? This will cancel. And then you get 1 over 9, or 0.111. That repeats, and that's molarity units. And that's actually what you need to do your calculation. Or you could leave it as 5 over 45. But since this one's at 0, when I do my change, right, guess what? I have to go the other way because I set it up so there was none of one of the ions. And so now this will be X. And those will be plus 2X. Like that. Okay? All right, so, yeah. Ooh, weird. The laser just showed up. I didn't do that. Like, weird things are happening. Hang on. Sorry. So this is going to be X. This is going to be equilibrium now. And this is going to be 0.111. See, I thought it would make it better for you there. Plus 2X like this. And so now KSP is equal to 0. What is it? 0. Oh, sorry. I had brain fart. X times 0.111 plus 2X squared equals, and then this is your KSP value over here. That's what I was like blanking on. Like, what is it equal to? It's over here. Okay, so now here's what you get to do. You get to solve it for X. But if you can assume X is small, and you can, and we'll prove it to ourselves in a second, then you can just assume that this is the same as X, right, times 0.111 repeating squared. And so now X becomes 4.87 times 10 to the minus 11 over 0.111 squared. All right, so that ends up being 3.94 times 10 to the minus 9. So that's the concentration of iron at equilibrium. Okay, sorry. That's equal to the concentration of iron. So again, it says what are the iron and hydroxide concentrations that remain when this happens. So the concentration of iron, that's 3.94 times 10 to the minus 9. And the concentration of hydroxide, right, is this number plus 2X. Now remember, we said X was small. And the way you can validate that is look at this number and see that it is substantially smaller. So if I take 0.111 and then I add 0.00000000394 to it, you get 0.111 back. Okay. And so that's your molarities of the two ions. Now the question is, how much precipitated, right? Because I didn't ask that, but I should have asked, how much precipitates? Well, basically, this much precipitates. Oh, sorry, not that much. This much is precipitating up here. All of that is precipitating. So you have 10 millimoles of precipitate that comes out, because really what dissolves back is almost nothing. So whichever one was your limiting reactant in the first part determines how much precipitate formed during the reaction. And so if I wanted to know, like, precipitate, it would be 10 millimoles of Fe OH2 formed. And if you needed to know that in grams, then you would find the molar mass and multiply it out. Okay, so those are all the various permutations actually of that problem. One will be like how much precipitate forms, how much is the iron concentration, what's the hydroxide concentration. These problems are pretty lengthy and take a little bit of thought actually to get through. But every single one of them is essentially done this way, where you figure out what it would be as a limiting reactant situation. That's the first ice table. And then you calculate back to equilibrium. Okay? And then, because we did this approximation where we shot all the way to the left of equilibrium, X will almost always be small. So you can go ahead and make a simplification like this. And when you look at your value for X, compare it to the concentration that it's being added to. And if it's not small, then what you need to do is actually set up a solver and solve for the value of X using a quadratic equation. Okay? Or whichever order equation happens to be. This one would be a third order equation.